Hey! 122! We're here today to go over practice exam 2 before the real exam 2 tomorrow. Hopefully you've taken the practice exam. I think it's smart to, give yourself an hour in a quiet room to take the practice exam. That's, the best way to practice is treat it like it's real. Let's go over this stuff. Here's the first problem. Oh, the practice exam says makeup exam, because, it's an old makeup exam I gave. Sketch a function that has all these properties. I like converting all this into a chart. I read this better if it's pluses and minuses on bars. What does f prime look like? What does f double prime look like? F prime switches at 3. F double prime switches at 5. What do I know? F prime is negative left of 3, 0 at 3, positive to the right of 3. What about f double prime? It is positive everywhere left of 5. It is 0 at 5, and it is negative to the right of 5. Was there any other information? Oh, there it is. Nope, that's all the information we got. So we don't know what f of any of these points are, right? We don't know what f of 3 is. We don't know what f of 5 is. So I can put those dots wherever. A thing to look out for on problems like this is, usually I describe it as you start by putting the dots and then you connect the dots with the right shape. We don't know where to put the dots, but I know the function is increasing between 3 and 5, so whatever you're doing at 3, you must be higher at 5. So I guess I'll draw it like this. What's happening to the left of 3? We are decreasing and we are concave up, so that is this shape. Between 3 and 5, we are increasing and concave up, so that is this shape. To the right of 5, we are increasing and concave down, so that is this shape. There's the 4 basic shapes. And I just want to make sure I'm doing the right thing on all of them. So left of 3, I need to look like this. Turn around and switch to like this. And then inflection point, do that. There we go. Anything that looks like that is fine. You could have drawn the graph lower or higher. I don't know where to put those dots. The x-axis could be up here, it could be down here. But because we don't know what f of 3 and f of 5 are. Usually on these problems I'll say what f of 3 and f of 5 are. I might have been making it a little trickier because it's a makeup exam. What else do we got? Find the critical points of this function, and then use the second derivative test. What does the second derivative test tells us? The second derivative test needs the second derivative. Let's take a couple derivatives. What's the derivative of this function? F prime of x is negative 9x squared minus 14x plus 0. F double prime of x is negative 18x minus 14. I want to find the critical points. When does f prime equal 0? If I factor an x out, I have two factors, either negative 9x minus 14 equals 0, or x equals 0. So there's one critical point. This one turns into negative 9x equals 14, so x is negative 14 over 9. Here's my two critical points. To use the second derivative test, I take those numbers and plug them into the second derivative. What's f double prime of 0? Let's do that down here. F double prime of 0 is negative 14, is negative. In my head, I'm thinking, negative second derivative means concave down. Concave down critical point, that's a local max. So, x equals 0. Is a local max. What's going on at negative 14/9? Oh, I should close that. Where is that open? I need to close that tab. Cool. F double prime of negative 14/9 is, this is going to be gross to plug in, negative 18 times negative 14/9 minus 14, 18 and 9 cancel, I get negative 2 times negative 14 makes positive 28, minus 14 is 14, that's positive. In my head, I think, aha, your second derivative is positive. That's concave up. Critical point when you're concave up. That makes a local min. There's the answers to the questions they asked. What else do we got? For this function, find the local extrema, the inflection points, when is it increasing, decreasing, yada yada yada. Hey, I'm aware that everybody taking this class should have a graphing calculator. So like just drawing a really good graph is not cutting it here. Like I'm grading you on, did you show me you're doing calculus to do all this stuff? What do I need to do? I need to find extrema, find inflection points. Those need inflection points because it's going to come from when does the second derivative equal 0. Local extrema are going to come from when the derivative equals 0. Those aren't the local maxima minima. Those aren't the inflection points. Those are the points that might be the maxima minima inflection points. That's like a big point of this exam, is just knowing that where the derivative equals 0 is not enough. You got to do something after that, but let's find the derivatives. Derivative of this function. This is something times something. I got to use the product rule. Derivative of the first times leave the second part alone, plus leave the first part alone, derivative of the second part. This is e to the something times derivative of the inside will be 2. I can factor the e to the 2x out. What am I left with inside? 1 plus 2x. I'm going to set that equal to 0 in a second. First, let's take the second derivative while I'm in a derivative taken mood. Again, this is something times something. So again, the product rule. I can use this line or I can use this line, whichever one seems easier. I like the bottom one because then it's just one product rule. Derivative of the first, that's 2. Leave the second part alone, e to the 2x. Plus, leave the first part alone, 1 plus 2x. Derivative of the second, what's the derivative of e to the 2x? It's e to the 2x times 2. If I factor out that e to the 2x, I get 2 plus 1 plus 2x times 2. What is this going to be? That's 2 plus 4x e to the 2x. That's 4x plus 4 e to the 2x. I want to know when do these things equal 0. This thing's already factored. It's going to be 1 plus 2x equals 0, or e to the 2x equals 0. E to the 2x is never 0 because it's always positive. This gives me 2x equals -1, x is -1/2. This one, when does f double prime equal 0? That's when 4x plus 4 equals 0, or e to the 2x equals 0, but e to the 2x is always positive. E to the anything is always positive. So when does 4x plus 4 equal 0? 4x is -4, x is -1. This is our only subcritical point. This is our only critical point. These are probably an inflection point and a local max or min, but I don't know that yet, and I need to know increasing, decreasing, so I'm building the whole big sign chart anyway. Do I need to make a sign chart for f? It doesn't ask for intercepts and it doesn't look for a graph, so I think f prime and f double prime are all I need to answer the question. F prime is 1 plus 2x e to the 2x. F double prime is 4 plus 4x e to the 2x. My points of interest are -1 and 1/2. -1 is left of 1/2. -1 is a point of interest because that's where the second derivative equals 0. F prime is a point of interest because that's where the first derivative equals 0. What's happening around these points? If I take f double prime of -2, I'm going to get -8 plus 4 times e to the something. That's a negative times a positive. I wrote -1. It's not -1, but it's negative. A negative times a positive is negative, so I'm negative on this interval. What's f double prime doing to the right of 2? Let's take f double prime of 0. It's going to be 4 plus 0 times e to the 0. That's a positive times a positive is positive. We're positive to the right of -1. So -1 actually was an inflection point. Now I can do the thing where I stare at this point and ask what's going on. when I imagine what y equals f prime of x looks like, I know that f prime equals 0 at this point, and its derivative is positive. This thing I'm imagining is not f. I'm imagining f prime. The second derivative is positive, and the first derivative is 0, so we increase through 0. We must have been positive to the right and negative to the left. I don't think I talked about this during the lecture, but you can do the same imagining if you think about what f looks like. F, I know, has a critical point, and I know f double prime is positive, so I know I'm concave up. I guess this is the second derivative test. Once you know that the second derivative is positive, then the f is concave up, so you must have been decreasing to the left and increasing to the right. I can imagine what f prime looks like, or I can imagine what f looks like. Either should get me to the same place. It's negative to the left, positive to the right. Or I can just plug points into the first derivative. Like, this is all... I belabor this point so much for the fact that it's saving us so little. We just needed to plug a couple points into here the same way we did here and here. We get that it's negative to the left, positive to the right. I think we can answer all the questions they asked. When is it increasing, decreasing, concave up, concave down? The function is increasing when the first derivative is positive, so that's 1/2 to infinity. When is it decreasing? It's decreasing when the first derivative is negative, that's negative infinity to 1/2. These bracket parentheses things don't actually matter that much. That's not a thing I'm grading on. If they ask when the... yeah, I'm going to stop myself from talking about it. They don't matter. Technically, the correct answer is closed bracket, but an open bracket is a also correct answer that every book says is the more right way to say it. When is it concave up, concave down? Concave up on when the second derivative is positive, so that's -1 to infinity. We're concave down on negative infinity to -1. Again, bracket parentheses don't matter too much. Infinity always gets parentheses because it's not a number. Is that everything they asked for? Oh, the maximum minimum inflection points. X equals 1/2 is a local min, and x equals -1 is an inflection point. Cool. This problem goes really wrong if you mess up on the derivatives. Don't freak out too much if the thing you're getting as your solution doesn't match the answer. Like, don't... I'm mostly grading you on can you make this chart and can you read information off of this chart. Getting the derivatives wrong will mess up the chart. You will get more points for correctly doing the chart than you will for looking at the graph and trying to interpret the chart wrong to match the thing that, like, whatever the function looks like. You can see where it's concave up, concave down. I'm not grading you on your ability to look at a thing your calculator gave you and read off when it's concave up, concave down. I'm grading you on your ability to take the derivative, which you're likely to mess up. They're hard, and we didn't get to do a gateway exam in this class. But take your derivatives, build the sign chart, read the information off the sign chart. The more you're doing close to the correct thing there, the easier it is for me to find points to give you. That's the thing to focus on when you're taking this exam. This problem sucks. This exam is really hard, by the way. This is the hardest of the 3 exams. It gets way easier after this. You probably saw that at the Chapter 5 stuff is a lot easier than the maximum minimum stuff. What's this problem? Find the global maximum of this function on this region. This is mostly an issue of take the derivative, set it equal to 0. But also we want to say something about how do we know it's a max. We're on the region x greater than 0, which is good because I can't plug in 0 because we'd be trying to divide by 0. Our function is 4x plus x to the -1. The derivative of that function is 4 minus x to the -2. We'll go ahead and take the second derivative in case the second derivative trick works for knowing that it's a max min. The second derivative is positive 2x to the -3. That's 2 over x cubed. This thing's always positive. Second derivative always positive says this graph is concave up for the whole interval. I don't actually know it has a minimum like this. The graph might look like this. It might just look like this. But it's some version of always concave up, and in all these cases, it doesn't have a maximum. Right? So we get to know right away there's no maximum. When does the first derivative equal 0? That's at 4 minus 1 over x squared equals 0. That's 4 equals 1 over x squared. That's 4x squared equals 1. That's x squared equals a fourth. That's x equals plus or minus the square root of a fourth, which is plus or minus a half. And I don't care about the negative one because I'm only looking at the region where x is positive. The second derivative was positive. Always. So any critical point is a max. Wait, hang on. Concave up is a global min. So we have a global min at x equals a half. We have no max. We can hopefully look at a chart, look at a graph on a graphing calculator and confirm that. But again, I'm grading you on did you do the calculus. I think it's fine to use the calculator to check your work, but the calculator is not going to get you around doing the work, I don't think. I got a cost function. I got a selling price. We need to write the revenue function. If you sell the thing for $2.22, revenue is price times quantity. So my revenue is 222Q. What's the profit function? Profit is revenue minus cost. So profit is 222Q minus the cost function is 50,000 plus 3Q squared. Distribute the minus through, and I can write that as 222Q minus 50,000 minus 3Q squared. Check, check. Find the quantity to reduce in order to maximize profit. In this context, we don't care as much about did you prove that you showed your work, and this problem's not explicitly saying show how you know it is a maximum and not a minimum. Here it's just enough take the derivative, set it equal to 0. What's the derivative of profit? It's 222 minus this constant goes away, minus 6Q. When do you equal 0? That's when 6Q equals 222. That's when Q is 222 over 6. That's 111 over 3. That's 37. 37. There's our Q value to maximize profit. Q equals 37. D says, what is the maximum profit? I take that number and plug it into the function. What's profit at 37? It's 222 times 37 minus 50,000 minus 3 times 37 squared. What is that, dear calculator? What is 22? Hey, wake up. 222 times 37 minus 50,000 minus 3 times 37 squared. Negative 45893. The best we can do is be 45,000 in the hole. Cool. It's a little disconcerting that our profit is negative. That's fine. It doesn't change the math at all. 6. This feels like a Goldilocks thing. At a production level of 5,000 units, I know my marginal cost, I know my average cost, I know my marginal revenue. If I want to increase my profit, what should I do? This is where I think about marginal cost versus marginal revenue. The next item I make costs me $60. The next item I make brings in $66. Will making extra items help my profit or hurt my profit? The next item I make will bring in more than it costs, so my profit will go up, so I should increase production. You can write down a whole long sentence like I just said, but the emphasis is, like, the thing I'm looking for is marginal revenue versus marginal cost is what we compared. This is all you need to say about why marginal revenue is higher than marginal cost. B, should I increase or decrease production if I want to lower my average cost? This is where I compare average cost to marginal cost. Is the next thing I make going to help the average or hurt the average? I want my average cost to be lower. The next thing I make costs 60, my average is 50. Like, if I'm in a class and my average is 50, and I get a 60 on the next test, did that help or hurt my average? It brought my average up, which would be good in a class, but it's bad for business because I want to lower my average cost. We should not make the next item, and we shouldn't have made the last item. We should lower production. I guess it's worth adding to this one was to increase profit. This one is to lower average cost. Why? Because the average cost is less than the marginal cost. C. What's my total cost at 5,000 units? This is about what does average cost mean. Average cost is total cost divided by production. Telling me that at my production level of 5,000, my average cost is 50, tells me that the total cost of making 5,000 units, like I'm paying $50 per unit on item, I'm paying $50 per item on average, and I made 5,000 of them. So 5,000 units that cost $50 a piece on average will cost 5,000 times 50 is 25 with an extra zero. That much total. And like this equation can justify why do you multiply by Q? I'm getting the C by itself. What's up next? I got a graph. Hey, that looks suspiciously like the graph from the last test. At a production level of Q equals 300, at this production level, should we increase or decrease production to lower our average cost? This is why the same Goldilocks where I want to compare the marginal cost versus average cost. But now these are both slopes that I can look at from the graph. The marginal cost is the slope of the tangent line. It's the derivative. That's this slope. The average cost is the slope of the line from 0, 0 to that point. I scratched the line out. Which one's bigger? The average cost line is steeper. Don't worry about trying to copy the graph down really exactly, but do copy it down enough that you can draw these two lines and show me that you saw the one was steeper. Like, the thing I want to see is, were you looking at the correct lines? That's what I'm looking at. Average cost is bigger than marginal cost at 300, so the next thing I make, this is how much it costs to make one more, is cheaper than the average one. The next one I make will be cheaper than average. Making it will bring down the average, and we want to bring down the average. So we should increase production. To lower our average cost. There's not supposed to be a comma there. But I wanted to get rid of the period. So that's part A. Part B, when do we minimize our average cost? This is the thing where I think about all the lines coming out of here and how high can I tilt this line up? When is the first time I'm actually going to hit that graph? So I hold one end of my ruler at this point, and I tilt my ruler upwards until I just barely graze the graph. If I can hold my dot here, I think it's like about like that. If I tilted it up a little bit more, they would be intersecting at this point. Looks like average cost is minimized around almost 800. I'm going to call that 790 units. Is how many I should make to minimize my average cost. I can see to the left of here my marginal cost would be less and I should increase production. I can see over here my marginal cost would have been bigger and I should lower production. And those are both pointing me towards the spot where it just barely grazes is where the two things are equal. Cool. Let's talk about elasticity. What I sell at $11 a piece, I can sell 25 a day. The next day, if I sell 12 a piece, I only sell 22. Estimate the elasticity of the demand. We saw two formulas for elasticity. This one is probably better off with the percent version of elasticity. Elasticity is the opposite of the percent change in quantity over the percent change in price. Do I have this right? I always get this wrong. I get this wrong often enough. I'm going to stop for a second and double check that I have this right, because yes, Q on top, P on bottom. How much did our quantity change? Our quantity went from 25 down to 22. So our change in quantity is -3. But I want, what is that as a percent? As a percent, I lost 3 out of, I started with 25. 3 out of 25 is -12%. Sales went down by 12%. I need to be able to work out a percent. How did my price change? My price went from 11 up to 12. So the change in price is +1, but I want the percent change in price. It went up by 1. Out of the 11 was my original price. 1 out of 11 is like 9%. I guess I should get digits on that. The calculator. What's 1 out of 11? It's 9.09%. So my elasticity is negative percent change in Q over percent change in P. The negatives cancel like they always should. Elasticity should always be positive unless you have conspicuous consumption going on. 12 over 9.09 is, what's 12 divided by 9.09 is about 1.32. The elasticity is 1.32. That means demand is elastic. Should I increase or decrease the price to increase my revenue? I always have to reason through this. My elasticity is big. I have a big top and a little bottom of this fraction, if the fraction is ending up big, or the top is bigger than the bottom. I had a small change in price that made a big change in sales. So increasing the price by a little bit will lower sales by a lot. That is bad for my revenue. On the other hand, decreasing the price by a little bit will increase my sales by a lot. That's good for my revenue. That's what I should do. We should lower price to increase revenue. You can memorize the relation that bigger than 1 is lower price, or I can never remember that, so I stare at the fraction and reason it through. Here's the other version of elasticity. The other formula for elasticity is negative dq dp times p over q. What is dq dp here? Q is this formula. The derivative of that function is negative 11. So elasticity becomes negative 11 times p is p over q is 10 minus 11p. I get 11p over 10 minus 11p. Cool. There's my formula. I guess I'll write it up nice. This problem could also say, what's the elasticity at a number? So you're plugging in a number. Is demand elastic or inelastic at that price? So you're checking whether elasticity is bigger or less than 1. Should you increase or decrease whatever? We could ask the exact same questions here, where we said, what is the elasticity at this particular price point? You get that by plugging in this number. I'm sure you've seen that in the homework. Let's do a Riemann sum. I want a left endpoint Riemann sum. N equals 4 is telling me how many pieces I should cut the interval to. I'm starting with the interval from 1 to 9. That's an interval of length 8. I want to cut that into 4 pieces. So 8 over 4 is going to be my delta x is going to be 2. I'm cutting it into pieces of length 2. My 4 subintervals are from 1 to 3, 3 to 5, 5 to 7, 7 to 9. How do I get a left endpoint Riemann sum? I need to pick a point from each of these intervals and plug it into the function. My point is going to be the left endpoint, because they said it's a left endpoint sum. I need to plug these numbers into the function. To plug it into the function, I square it, subtract 3. I need to multiply each of these by delta x, and then add them up. Because the delta x's are always the same, I can add them up and then multiply by delta x. What's 1 squared minus 3? It's negative 2. 9 minus 3 is 7. 25 minus 3 is 22. 49 minus 3 is 46. Add these up. I got 20, 27, 67. I think I'm getting 73. 2 times 73 is 146. There's my left endpoint Riemann sum. Ooh, definite integral time. We're being given the marginal cost of something. We're given the rate of change of marginal cost, or we have marginal cost, which is the rate of change of cost. We want to know, what is C of 700? How do you go from rate of change to a value? That's what the definite integral does. C of 700 minus C of 0 is going to be the integral from 0 to 700 of C prime of Q. To find how much the total change was, you do a definite integral of the rate of change. You want to know how much did it increase between 0 and 700? You're doing this integral. We want to know, what is this area? I don't have a function I can plug into my calculator to compute the integral. I don't want to deal with the Riemann sum. I'm trying to estimate the area. This is the thing we do by counting boxes. How many boxes are completely in this region? I have 1, 2, 3, 4, 5, 6, 7, 8. That looks like it's completely in. 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 20 boxes inside. Plus, how many boxes are partially inside? This is most of a box. This is part of a box. Part of that, 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 part of that. We're doing the thing where we say, on average, some of these boxes are mostly full, some of these boxes are mostly empty. Assume that they are averaging out to be halfway full. This tends to be more accurate than a thing that human eyeballs are good at estimating. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 partial boxes that I'm going to estimate as half a box each. That's how much credit I'm going to give them for. So 20 plus half of 10 is 30 boxes is our estimate for the area. So the area is the integral from 0 to 700 of marginal costs. Is how much is 30 boxes of area? Well, how much is a box? A box is 100 by 200. So that's a 2 with 4 zeros after it, 20,000. So 30 boxes at $20,000 a piece. Dollars? Are those the units? Yeah. Because it's dollars per unit times units makes dollars. Is 6 with 5 zeros after it? 600,000. So the total change between 0 and 700 was 600,000. If we started at 100,000 as our cost, and our cost is increasing by 600,000, I would say that C of 700 is about 100,000 plus 600,000 is 700,000. Maybe you didn't agree with me on some of the partial boxes, or maybe you said this should count as a partial or a half. That doesn't matter so much. I'm expecting something in the ballpark of 700,000, but show me that you're counting boxes. Show me that you multiplied by the area of the box. Show me that you're doing the right type of thing. I don't care if you're getting the exact same number as me. And last one is number 12. Area bounded by a region. I want the total area bounded by the curves y equals natural log x and y equals x minus 1 between 1 and 2. What do these look like between 1 and 2? Why did I draw two vertical lines? Here's x equals 1. Here's x equals 2. I know what x minus 1 looks like. It's going to look like this, right? Do I know what natural log x looks like? Maybe I should just graph these things and get a sense of which one's on top and which one's on bottom. Show me ln x and show me x minus 1. Don't graph it everywhere. I really care what's happening between 1 and 2. So let's graph it between 0 and 3. We'll show what's happening between 1 and 2 pretty well. All these numbers are very small. Let's change the window to zoom in on these smaller y values. Just go from -2 to 2. Yeah, that's a little more visible. Okay, I want the area between these two curves. So one of them's the straight line. Looks like the curve bounces off of this at 1. So that's like a tangent line. I want to know what's the area between these curves between 1 and 2. So what's this area? To find that area, I need to integrate from left pinch point to right pinch point. I guess they're not pinch points here. Of the top function minus the bottom function. This is the integral from 1 to 2 of our top function is x minus 1 minus our bottom function is natural log x. I kind of need the graph to be able to tell which is the top and which is the bottom. I guess I could have just done it and seen if I got a negative answer, switch it around. I need to integrate this function. The way to integrate it is to graph it. I don't need these graphs anymore. I want to look at the thing I'm integrating is x minus 1 minus natural log x. Show me that. And now second trace is calculate. 7 is the integral from 1 to 2. I want 3 digits of accuracy, so that's 0.113. I guess that rounds up to 0.114. That's what we're doing. That's what's on the exam. If you have any questions or concerns, send me a message. I have someone asking if they can get more time on the homework. If you need more time, I don't need to do the exam on Friday. If you would rather wait until Sunday, that works for me. I don't want to wait until like Tuesday because we still have another exam after this one. Send me a message if you need more time. I guess I'll send you guys a message saying, hey, let me know if you need more time. I'll see you guys around.